Good morning, everybody. So before reading week, we were talking about declaring stuff in C. At the end of the last lecture, we were talking about using a header file to declare a function and then including that header file into your programs so that your program can actually use the header file. And so just to quickly remind you what was going on, we had this file called max2. So we had a function called max2, and it was defined in its own file max2.c. So max2 takes computes the maximum of two double values and returns the larger of the two. And then we wrote a little program called bad uses max2. And bad uses max2. It defines its own function called max3, so that's fine. We have a function called max3, and we want to use max2 from max2.c. And so our solution, which is the incorrect thing to do, was to include max2.c in our bad uses max2 file. So by including max2.c, remember what include does, it basically takes the contents of max2.c and pastes it into your file. So the stuff I've got highlighted here effectively replaces the include right there. Right? And that makes max2.c available to our program now. And so max3 can now use it, so it uses it there. And everything seems to work fine. So in other words, if you compiled bad max2, it seems to work, which is, I guess, good, but it turns out it's actually bad. So what you should never do is you're never supposed to include the contents of a C file inside of another C file. And the reason you don't do this is because you can inadvertently include the same file twice. So imagine you write another program, it includes max2.c, but it also includes another header file, or it includes another C source code file, which also includes max2.c. So what ends up happening is that you end up with two copies of max2.c in your program, and then your program no longer compiles, right? In C, every function can only be defined exactly once, right? There's another example of this. So, oops, sorry. Control. Oh, there we go. All right, so I've got some header files made up here. So there's something called grandparent.h. So inside the header file grandparent.h, there's a definition and a declaration of a variable called x. So this says that x is an int, its value is 1. Any file that includes grandparent.h gets access to this one static instance of x. Right, remember x is declared at file scope, so it has a static linkage, which means it's available to every other compilation unit. Right, so anybody who includes grandparent.h gets access to this global variable x. Right, you now have another header file called parent.h. Right, parent.h includes grandparent.h. Right, so this turns out to be very common. It's very common for header files to include other header files. Parent.h declares the global variable y. And now finally you've got the child file, and it includes both header files. Right, so it includes grandparent.h because it wants to use x from grandparent.h. It includes parent because it wants y from the parent, right? And now what's the problem here? So the problem is because parent includes grandparent, you end up with two instances of int x equals 1. So if you try to compile this program, you now get an error, right? And it tells you you're redefining x. Right? Why? Because you've included the header file grandparent h twice, right? Which you want to avoid doing if you can. Now, what you don't want to do is you don't want to have to sift through all your header files and see, well, what header file is this header file including, and then deleting the unnecessary includes. That won't work anyway in a large program. So the solution is that you need some way to tell the compiler not to include a header file more than once, right? And that's what an include yard is. So if you go back to declarations notebook, you'll see that inside, whenever you create a header file, you should also include what's called a header guard. So the header guard typically looks something like that. So it's a pair of preprocessor directives followed by a closing preprocessor directive here. So the first preprocessor directive is if and def, so if not defined. Right? And so this is asking the preprocessor to look for something called max2_h. Sorry, I don't know what that was. And so if max2_h is not defined, right, then everything inside of the if and def and if gets processed. Okay, so if max2_h is not defined, and then so there's another preprocessor directive called define. So define basically defines a name, right? So if you define the name max2_h, that simply says that the preprocessor is now aware of this name max2_h. Right? So if the name max2_h is not defined, go ahead and define it. Right? Now go ahead and declare your functions that you want to declare. So this declares max2. Right? The end if closes the first closes the if and def. Right? Okay, so that wraps up your function declarations and your variable declarations if they exist inside of an include yard. Now, if more than one file tries to include max2.h, or if your same file tries to include it twice, right? The first time it sees the if and def, right? Defines max2_h and then includes the function declaration. The next time the header file gets included, right? This is no longer true, right? max2_h is defined, so everything inside here is ignored. So that prevents your header file from being included more than once. That prevents any definitions that you have, like int x equals 1, from being included more than once in your program, and that allows your program to successfully compile. Right, so whenever you make a header file, you should wrap it up with an include yard that looks like this. There is a non-standard way to do this. There's a non-standard way to do this. Most compilers have a preprocessor, a special preprocessor directive that tells it to only include header files once. If your compiler doesn't have that sort of thing, you have to use this sort of if and def and if structure here. The problem with doing this is that your preprocessor names have to be unique as well, right? And so you need to come up with some scheme that lets you name your preprocessor constants like max2_h, right? And you have to hope that any other source code that you're using from an external source is using a similar naming scheme, right? Or because if someone else makes a header file and also includes names its header guard that, you end up with a problem. Right. So there's still this problem of that C has no mechanism to enforce unique names. Right? And that's why Java uses packages, or one of the reasons Java uses packages. Right? So in Java, you have a package and a class. The name of the class is the fully qualified package name plus the class name. And if you follow the Java package naming conventions, package names will be unique. And so that lets Java get around this one definition problem. There's your include yard. Okay, so now you know how to make a header file and create an include yard for your header file. Right. Okay, moving on. So that takes care of the declarations notebook. We're now in the statements notebook, which is pretty short because C statements basically look like Java statements, more or less. Let me quickly, yeah, so it's quite short. Okay, so a statement in Java is similar to a statement in C is similar to a statement in Java. It's just a chunk of a C program that's executed in sequence, right? So statements can be one line long, so like assignment, right? So that's an assignment right here, right? That's considered to be a statement, right? It's one line long, it ends with a semicolon. You can have compound statements too, just like you have in Java, right? So an if statement or a for statement, those are all examples of statements. Those are typically over more than one line. Okay, so assignment, exactly same syntax as there is in Java, right? That's declarations, x exists, it's an int, right? That's assignment, x gets the value 5. Right? Remember that if you have an array variable, so here x is an array, is a variable that can store an array. You are not allowed to assign to an array variable in Java, in C. And strings, remember in C, are just arrays of char, and so that means you can't assign to a string either, which causes all sorts of problems for new programmers. right? So here I've got a string 1, it's the string hello, right? Here's string 2, sorry, it's the string goodbye or bye, right? If you come from a programming language like Python or Java, right, it's very common to reassign strings variables, right? String s equals something and then s equals something else in the next line. You can't do that in Java, in C. Why? Because strings in C are simply arrays. You're not allowed to assign to an array variable in C. Right, so if you want to replace the contents of string 1 with by, you have to call a function to do it for you. Or you have to copy the characters in from the string 2 array into the string 1 array yourself. Right, so you have to do something like string 1, 0 equals b, string 1, 1 equals the y, and then string 1, 2 equals the e. And then don't forget, string 1, 3 equals the null terminating character. Right. There is a function that does that for you, which we'll look at when we talk about strings in greater detail. Right, so remember, you can't assign to strings because strings are simply arrays in C. Function calls work basically the same as method calls in C, in Java, except there are no class names in Java, and C, sorry. Right, so I guess function calls behave similarly to how they behave in Python, although C doesn't have all the nice things that Python has, like default parameter values and stuff like that. Right, so calling a function in C looks like calling a function in Python, right, or calling a method in Java without using a class. So here we're using the sine function, and here we're using the cosine function. Again, nothing new here. The compound statements in C are identical to the compound statements in Java. There's an if statement, right? The if statement looks exactly like it looks in Java, right? So this one, what's it doing? We have the value 100. We're going to compute the remainder after dividing value by 2. So we're checking if it's even or odd. Right? So if the remainder is 0, it's even. Else if, right? Exactly the same as in Java, it's odd. Sorry, if the remainder is less than 0, it's negative. Right? The else part here should never happen. Right? Oh no, odd and positive. Yes, sorry. I'm sorry, I'm being dumb. The else part here tells you that it's odd and negative. Right? Sorry, odd and positive, this is odd and negative. Right? But this is an if statement in C, right? Exactly the same as in Java. Java has a switch statement. I never show it to you in 124, but the switch statement is similar in C to the Java switch statement. Right, click on that link there if you want to see how to use a C switch statement. It's basically, it lets you implement a big if, else if, else if, else if chain using a simpler type of statement called switch. Right. There are loops in C, the while loops and for loops. They are identical to the while loop and the counting style for loop in Java. Right, so here's a while loop that counts from 1 to 5 or something like that. What does it do? Oh yeah, this has to be in a main function, sorry. So it starts counting at 1, it stops at 6 apparently in this case. So if this actually compiled in rand, it would count up to 6. Right. There's a do while. There's also a do while in Java. Again, I don't normally show it to you. The difference between do while and while is that while checks its condition before the loop runs. Do while checks its condition at the end of every loop iteration. Right, so a do while loop runs once, is guaranteed to run once. A while loop may not run at all. Right? Otherwise, they're exactly the same thing. And finally, for loops in C, there are no enhanced for loops in C. Right? So you can't use the for each type loop that you can in Java. So you have to use the counting style loop in C. Right? And so there is a loop that counts from I starting at the value start, so 1. Right? The loop runs as long as I is less than or equal to 6. Right? Inside the loop, you print out the value of I, so 1, 2, 3, 4, 5, 6. Each time at the end of the loop, add 1 to I. Right? And then finally, there's a break statement. So I think finally, oh no, there's a break and continue. Right? So again, just like in Python and Java, C has a break statement which lets you break out of a loop. Right? So this one counts again 1 through 6. Or 1 through 5 in this case. Yeah, 1 through 5 in this case. Right? So here we have while 1, which is interesting. You can't do this in Java. Right? In Java, you need a Boolean condition here. Right? But remember in C, C considers Boolean values. C Boolean values in C are basically integers, right? So anything that's 0 is true. Anything non-zero is, anything 0 is false. Anything non-zero is true. So that in C means while true, right? So while this is true, if I is greater than 5, you can break out of the loop, right? So that stops the loop from running. It behaves the same as in Java. It breaks out of the loop that it's defined in, right? So this breaks out of this loop, out of the while loop here. If that while loop was inside of another loop, it does not break out of the outermost loop. Right? And finally, there's a continue. I think that's final, yes. Right? So continue lets you skip a loop iteration. Right? And so this one uses a loop to count from 0 to 9. Right? It skips the iteration when I is equal to 5. Right? So when I is 5, it does nothing. It continues. So it jumps back up to the next loop iteration. Right? So this prints out 0, 1, 2, 3, 4, skips the 5, 6, 7, 8, 9. Right? And so statements in C, assuming you know your Java reasonably well, they're exactly the same as statements in Java. Okay, any questions so far? Yes?
Would you go back to the if?
I sure can. Yep. In the previous...
And right there, just go to the if section.
Here?
At the beginning.
At the beginning, okay. Here.
Yeah,
yep.
Puts?
Oh, puts is, puts will print a string to standard output, but it only prints one string. So that prints the string even, that prints the string odd and negative, that prints the string odd and positive.
Is it the same thing as just printf?
It's not the same. Printf lets you print whatever formatted data you want. Puts will only print a single string. Yeah, it's only one string, so you can't like put in a comma here and something else, right? Yeah, it won't let you do that. So it's not like Python's print. Yeah. Okay, integers. Let me just quickly check what's going on in this notebook. Oh yeah, okay, so this is. All right, this notebook tells you about C's integer types, but it also tells you how most modern computers represent integers. So we're going to talk about something called 2's complement in this lecture. All right, so integers in C are similar to integers in Java, right? The types are they even have similar names, right? There are some important differences, which we've already talked about, right? So remember, the C standard doesn't specify how integer values, how they're represented. Although this was supposed to change last year, I don't know if it actually did. So it doesn't specify how integer values are represented, and that's a bit strange. So Java says that all of its integers are represented in what's called 2's complement. C doesn't say that because C is an older language, right? Born in the 70s. Back in the 70s, different computers would represent integers in different ways, right? And so your most significant bit might have been at the end, it might have been at the front, right? And the way that you represent signed values, there were at least 3 different ways to represent signed values. So there's no standard way in the old days of representing even simple integer values. Nowadays, almost every modern computer uses something called 2's complement. So the standard is going to try to evolve. It's probably going to say in some time in the future, or if it doesn't already, it's going to say that integers are considered to be 2's complement. It still doesn't say, though, how big is each type, right? And so it is still possible to have an int on one computer be represented using more or fewer bits on another computer, right? And so remember, C only says, it doesn't say exactly how many bits are used to store a primitive, to store of type, right? It simply tells you the ordering of the types, right? So char is the smallest, then short, or is that true? Then short, yeah, and then int, and then so on and so on and so on. Right? C has more integer types, so we've seen that already, and in particular, C has unsigned types. Right? And the other one that it probably won't cause you guys any difficulty because you don't do a lot of this in Java, right? So in Java, you only really, in 124, you really only use int, sometimes you use long, but you never use the other integer types. in C, the C compiler will convert between the different integer types, even if you're converting from a wider type to a narrower type, right? So if you have a long value, the compiler may let you store that in an int value, and it may not tell you that there's a problem. Right? So the compiler is more permissive than Java's compiler when converting between the integer types. In particular, you can convert any Boolean type to integer, and you can convert any integer type to Boolean. Okay, so here are the integer types. Right? We've seen this before, right? Notice there's a bunch of them, but the reason there's so many of them is because there's a signed and an unsigned variant for most of the types. Right? So you have a signed car, you can have an unsigned car, you can have a plain old car. Right? You can have a short, unsigned short, or plain. Short and unsigned short, right? You can have int and unsigned int. You can have long and unsigned long, right? And finally, you can have long long and unsigned long long. Right. So again, remember the second column here, right? Notice that it tells you what is the minimum size of each type, but it doesn't say what is the actual size, right? The actual size depends on your compiler and your architecture. Right. I guess in today's world, on a desktop computer, you only really have to worry about Windows and not Windows. Right? So if it's Windows, some of these sizes are different than if you're not in Windows. And it depends on which version of Windows you're on. So if you have a 32-bit version of Windows or you have a 64-bit version of Windows. Right? But this problem is less severe than it used to be. If you want to know what the actual limits are on your types, they're defined in a header file called limits.h. Unsigned types. Okay, so unsigned types simply means that you can't have negative values, right? So your smallest value starts at 0 and it goes up to some maximum value, right? The unsigned type and the signed type, they always occupy the same amount of memory. So you have a signed car and an unsigned car. On my computer, they're probably both 8 bits, right? If you have a signed int and an unsigned int, on my computer, they're both 32 bits, right? So the signed and the unsigned variant typically have the same number of bits. And so what does that mean? It means that the largest unsigned int is bigger than the largest signed int, right? Because you don't have to represent all of the negative values with unsigned int. So you get to represent more positive values. There is the ordering. That's not, we've talked about that lots and lots. Oh, I guess I should show you this. Okay, so in today's world, there are what are called 4 common data models. And so there's this LP32, ILP. The names don't matter, right? So here's Windows. This is the data model that Windows 16 uses. Windows 16 is probably more or less dead right now. Windows 32 is still alive and kicking, right? So that uses the 32-bit version. Windows 64 is the current version of Windows, and then everything else. So Unix and Unix-like systems, and so that's Linux and Mac, right? And so there's a table up here that tells you how big each type typically is on these systems, right? Notice they're almost all the same, right? So these are all 8, these are all 16. There's a difference here with int, right? So on this is the 32-bit version of Windows, and int is 16 bits, right? On all other modern systems, it's 32 bits. Long is interesting, actually. So a long on most systems is 32 bits. Right. Java says that long is 64 bits and LP64. So this is all Linuxes and Macs using a 64-bit operating system. Also says long is 64 bits. Right. But you could be in the situation where you have a long value that's 32 bits and it's the same or has the same range of values as an int type, which can cause all sorts of problems. Right. If int and long are both the same, that means you can't use a long to deal with overflow in int values. And finally, long is also interesting. So there is a long type. On all systems, on all modern systems, it's 64 bits. And so that means a long is the same as a long in Unix and Mac. right? And so that means, again, if you have to deal with overflow in long, you can't actually use long to solve the overflow problem. Right? So strange, but this is the way it works in C. Oh, there's also, okay, so there are times when you are going to want to use, you're going to want to use an int, for example, right? And you want that int to be exactly 32 bits or exactly 64 bits, right? If you want to do that, there is a way to do that. There's a type called int_32t, which you can find in standard int.h. Right, so if you look at the documentation for that header file, you'll see that there's a bunch of predefined types that you can use that correspond to the exact number of bits in each type. Right, so there's an int _16t and int _, there might be a 64t, I don't know if there is or not, and so on and so on and so forth. Right, so if it's important for you to actually specify the number of bits in a value, there are types that let you do that. Okay, bool, remember, so C doesn't really have a Boolean type. A relatively recent version of the language, so C99, that's 1999 version of the language, did introduce a Boolean type, and it called it _big B bool. Right, so that lets you store the values 0 or 1. That only stores the values 0 and 1. Right, anything that's not 0, anything that's not 1 or 0 gets converted to 1. Right, so the 0 corresponds to false, and the 1 corresponds 1, 0, and 1. False and true. I think those are backwards. No, that's true. That's correct. No, I'm being dumb. False and true. Right. 0 is false. 1 is true. Right. And so we looked at this example before as well. Right. If you want to if you want an actual Boolean type and you want to use a name bool, just include standard bool.h. Right. That simply defines the name bool, and it simply says that bool is the same thing as _bool. And so there's your Boolean type in C. Right? Char is basically the same as char in, char in C performs a similar role as char in Java. Exactly how it works though is, in Java, Java says that char is something very specific, right? So it says that the representation of char corresponds to something called Unicode 16. C doesn't say that. C just says char is an integer type, it has a certain number of bits, and that's all it says, right? Char is what a string is typically made out of in C, although that's also not necessarily the case. So it's possible to create a string that doesn't use char as its underlying type. Again, we'll look at that later on. The standard says that char is equivalent to one of these two things. So a char can either be an unsigned char or it can be a signed char, but the standard doesn't say exactly which one it is, which is confusing. Right? It's up to the compiler to decide which type char is equivalent to. Right? So on your computer, char might be unsigned and it might be not, or it might be signed. Right? It depends on exactly, it depends on your architecture and your operating system. Okay, so the unsigned integers, so this is a bit new for most of us here. They don't exist in Python or in Java. Or if they do, you probably weren't told about them. They certainly don't exist in Java. I don't know if they exist in Python or not. Anyway, unsigned integers. So the unsigned integers are just integers, their smallest value is 0. Right? They go up to some largest positive value. Right? They also have the simplest binary representation. So I think most of you here know what binary numbers actually are, right? They're a sequence of zeros and ones, right? What do the zeros and one mean? Well, you just multiply those by a corresponding power of 2, right? And so when most people write down a binary number, they write it from left to right. The leftmost bit is usually what's called the most significant bit, right? So in other words, it's multiplied by the power of 2 with the largest exponent. The rightmost bit is usually the least significant bit. All that means is that it's multiplied by the power of 2 that's equal to 0 over here. Right, so that 1 is that 1 here. Right, the second one is the second one here, and so on and so on and so forth. Right, to compute the decimal value of a base 2 number, right, you just take the bit, the 0 or the 1, and multiply it by its corresponding power of 2. right? So that 8-bit integer is 1 times 2 to the 0 plus 1 times 2 to the 1 plus 0 times 2 to the 2, and so on and so on and so forth, right? Now, this is the way that most people write it. It's not the only way to write it, right? So in other words, you can start, this could be the least significant bit. So that could be 0 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 to the 2, and so on and so on and so forth, right? So we're not going to worry about that. I'm always going to write them from most significant bit to least significant bit. You sometimes have to worry about this, especially if you're working, I think, in networking, where in networking, it's common to have the bits flipped to the other way, but not important for us, right? So we're always going to write them left to right, most significant bit to least significant bit. All right, so that's called so your leftmost bit, most significant bit. Why? Because it's multiplied by the largest power of 2, right? That means it contributes most to the overall magnitude of the number. Thus, it's the most significant bit, right? Least significant bit is the rightmost bit. Why? Because it's multiplied by 2 to the 0, which is 1. It contributes the least to the overall magnitude of the number. Okay, so what is the smallest unsigned value that you can write down? Well, it's the binary number whose values are all 0, right? And that's equal to 0, right? 0 times 2 to the 7 plus 0 times 2 to the 6 plus 0, and so on and so on and so on. Right? Similarly, the largest unsigned binary value that you write down is all 1s, right? And so that's equal to 255 in this case, right? And you can easily prove by induction that the maximum value of an n-bit unsigned binary number is equal to 2 to the n minus 1. Right, so if you use what Dr. Meager told you about in your math courses, you can easily show that given an n-bit unsigned binary number, its maximum value is that. Right, it's a simple proof by induction. Okay, so that's the unsigned binary numbers, relatively easy to deal with. Right. So how are the signed binary numbers represented on a modern computer? So your signed integer numbers are represented in what's called 2's complement. Right? Okay, so if 0 is considered to be... Right, so signed integers have ranges that have a most negative value and a most positive value. Right? If 0 is considered to be unsigned, right, then the number of negative values is not equal to the number of positive values. Right? This turns out to be important later on. Right? So you have a signed integer number, right, and you're representing it in binary. If we're going to use 2's complement, it turns out that there are more negative values than there are positive values. Right? There's one more negative value than there's a positive value. Is that true? Or do I have that the other way around? No, it's true. Right? All right. So can you explain why? Anyone explain why? Okay, so if you have a binary number, right, each bit can be one of 2 different values, right? So the total number of possible values must be even, right? Makes sense. Okay, so if you're going to split up if you have all your negative values and you have all of your positive values, right, and you have a 0, right, and there are an even number of total values, right, it must be the case that if 0 is considered to be positive, right, I guess there's one more positive value than there are negative values. Is that true? I'm not sure which way it goes. I don't remember which way it goes now. Anyway, it's not super important. Yeah, there is one more positive value, that's right. Then there are negative values, right? Okay, so again, the standard doesn't say that it uses 2's complement. It's expected that C23 will say that it's 2's complement. I haven't checked to see if it actually did that. But every modern computer uses 2's complement for its signed integers. Okay, so in 2's complement, the only thing that changes is the value of the most significant bit, or the meaning of the most significant bit. Right? So in 2's complement, so here's the same binary number that we had before. Right? This time it's assigned value. So we're now working with 2's complement. right? Everything's the same except for the most significant bit, right? When you consider the most significant bit, you multiply it by the minus 2 raised to the power 7, right? So with this unsigned, that minus sign is a positive sign, or not there, right? If it's 2's complement, that minus sign, so the most significant bit is now multiplied by the negative of 2 to the 7, right? So if the first bit is 0, right, you have a positive value, right? Because the only way to get a negative value out of this is if that first bit is 1, right? So if you have a 0 here, you know the number is positive, right? The magnitude of the number is exactly the same as the magnitude of the corresponding unsigned binary value, right? So 0, 1, blah, 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 is equal to 107 if you actually carry out the multiplication, right? Okay, so if that first bit is a 1, right, you're going to multiply it by minus 2 raised to the power 7, and that's going to guarantee that the number is negative, right? So if your first bit is a 1, you know your number is negative, right? And in this case, so if you flip the first bit to a 1, right, you're going to add minus 128 to the value, and now you get minus 21, right? So that 107 is equal to, subtract 128 is equal to minus 21, right? So if the first bit is a 1 and it's a signed number, you know it's negative. Okay, so now, what is the most positive 2's complement number that you can write down, right? So the largest 2's complement number that you can write down, well, the first bit can't be 1, so it has to be 0, right? Because if it was 1, you'd have a negative number. So the largest 2's complement number that you can write down is a 0 followed by all 1s, right? So here we have a 0 followed by 7 1s, and that's equal to 127, right? Now what's the largest, or the most negative value that you can write down, right? So the most negative value that you write down, well, the first bit has to be 1, right? And now all your other bits are 0. Because if one of these bits is not 0, you're going to add a positive value to a negative value, right? And that'll make it a larger, increase the magnitude of the number. Sorry, that'll make the number less negative, right? It'll move the number towards 0. So the most negative value that you can write down is a 1 followed by all 0s, right? So largest value, 0 followed by all 1s. Most negative value, 1 followed by all 0s, right? And if you compute that, you get minus 128, right? So notice the most negative value, minus 128, right? The most positive value, 127. Right? Strange, right? The range is asymmetric, which is what I was trying to get to earlier in the lecture, right? Your most negative value, its magnitude is greater than the most positive value that you can write down. This is a problem, right? Why is it a problem? Right? So suppose you have some signed integer value x, right? You do not know for sure if negative x exists, right? Because if x is minus 128, right? The mathematical value of negative x is 128. And guess what you can't represent in 2's complement? You can't represent positive 128, right? So you can't even guarantee that negation gives you back the correct answer, right? Similarly, you can't guarantee that the absolute value of x exists, right? Again, if x happens to be minus 128, the absolute value is 128, which doesn't exist in an 8-bit 2's complement number, right? Minus 1 times x doesn't exist for the exact same reason. X divided by minus 1 may not exist, again, for the exact same reason, right? Right? So weird, right? So math in C, well, math in any C-like language doesn't behave like math in the real world, right? Especially when you're working with the integer values, right? With the integer values, you always have to realize that overflow can occur, right? And in these cases, on most computers, overflow will occur. Now, the weird part is that C says that all of those result in what's called undefined behavior, right? So the C standard doesn't say overflow occurs, it simply says anything can happen. That's what undefined behavior means, right? So undefined behavior means the compiler can do whatever it wants. Oh, sorry, the compiler plus the runtime can do whatever it wants in this case. Right? And so if you ever see something in C that says undefined behavior, you have no idea what's going to happen. Program might crash, it might run, you might get the wrong result, you might get the correct result or the expected result. Probably not. But anything's allowed to happen. Right? So what exactly happens on my computer? Here we go. Okay, so I'm going to use sine car. Right? The most negative value for sine car is defined in a constant called scar underscore min. You don't need to remember that. Right? That's defined in limits.h. Right? I can't plug in a number here, like minus 128, because I don't actually know what it is, right? It depends, I'd have to go and look it up. So I'm gonna use the predefined constant instead, right? So if you print that out, I think it is minus 128 on my computer, so let's see what we get. Yes, it is. Okay, so here I'm going to negate C, right? So remember, this is the most negative value that you represent. What happens when you negate C, right? Well, you expect to get 128. Right? 128 is greater than the largest value sine car can hold. So what ends up happening? Well, we get minus 128 again. Right? So you can take a negative number, multiply it or negate it, and get a negative number. Right? What's happening? What's happening here is actually overflow is happening. Right? And so when it does the negation, you get 128. That's 1 greater than 127. So you get wraparound, and that goes back to minus 128. Right? If you want to compute the absolute value of a number, you include standard lib.h, not math.h. You'd think you'd include math.h. You don't. You include standard lib.h for some strange reason. Right? And so that lets you compute the absolute value of an integer. So the absolute value of minus 128 is minus 128. Right? If I multiply minus 128 by minus 1, I get minus 128. And if I divide a negative number by minus 1, I get a negative number. Right? So again, overflow bites you in the butt here. You have to be at least aware that this might happen to you. Right? Okay, so why is this happening? It's simply a consequence of the fact that we're using 2's complement as the representation. Right? Can you get around this problem? The answer is yes, you can, but not using 2's complement. You have to use a different representation of signed numbers. Right? So in particular, you can take one of your bits and use it as the sign bit. Right? So if it's 0, it's positive, it's 1, it's negative. Right? Now your range of numbers is symmetric. So now you can go from minus 127 to positive 127, and now that you can guarantee that negating a value gives you back a positive value. Changes the sign of the value. Right? But you have to use a different representation. If you switch to that representation, the range of values that you can represent is smaller. It also complicates the hardware that your computer has to implement. So it turns out 2's complement, the hardware is quite easy to, is relatively easy to implement. Okay, so what is the relationship between x and minus x in 2's complement? Right? So ignoring the most negative value, right? Because the most negative value, it always behaves funny in 2's complement, right? If you want to compute minus x, there is a way to do it, right? So the way to compute minus x given x is you take the bits of x and you flip them, and then you add 1, right? So here's the value, right there. That is 1, right? It's equal to 1. All zeros plus 1 times 2 to the 0, right? So I claim that to negate this value, I can simply flip all the bits. So zeros become 1s and 1s become zeros, right? So flip the bits and you get all zeros and then a 1, right? After you flip the bits, add 1 to the flipped bit number, right? Now adding 1 in binary is exactly like, so adding 2 binary numbers is exactly like adding 2 decimal numbers, right? So the long arithmetic or the long addition algorithm that you were taught in grade school is exactly the same, right? You have to compute a carry value every time, right? So I'm gonna, all zeros and a 1, I'm gonna add 1, right? So, sorry, all ones and then a 0. And now I'm going to add 1. So 1 is all zeros and a 1. So 0 and 1 is 1, right? 1 and 0 is 1, and so on and so on and so on and so forth. And so now I get all ones, right? So all ones in 2's complement, right? It's not the most negative value, it's -1, right? Remember that 1 means times -2 to the 7, right? So that's -128. The rest of these values are all adding positive values, right? It turns out if you sum all those values, you get 127, right? And that's equal to -1, right? So the 2's complement number that's all ones is -1. Right? Okay, so let's look at another example. So here I have 56, right? So it's zeros, some ones, and then some zeros, right? I would like to compute -x, so flip the bits. So you get 1, 1, right? Ones become zeros, so 0, 0, 0. Zeros become 1, 1, 1, 1. Now add 1. Right? So 1 is all zeros and a 1. Okay, so when you compute this, it's 1 plus 1, right? So this is exactly what you learned in grade school. 1 plus 1 is 2, or 0, carry the 1. Right? So 1 and 1 is 0, carry the 1. So now it's 1 plus 1 plus 0, which is 2, or 0. Carry the 1. Right? 1 plus 1 plus 0 is 2, or 0. Carry the 1. 1 plus 0 plus 0 is 1. And now you have 0, 0, 1, and 1. Right? So the algorithm is exactly the same. Now you have to compute a carry bit, right? Every time this exceeds 1. Right? And now you get the value. If you crunch all that out, you get -56, which is in fact the negative of the 56 up here. Oh, sorry, of the 56 up there. Right? So compute a negative value. If you're given a value in 2's complement, to compute its negative value, you can flip its bits, right, and then add 1. The reason this is useful is because in hardware, this is easy to do. Right? So in hardware, it's relatively easy to flip all your bits and then add 1 to the resulting number. Right? Whereas if you couldn't do that, computing negative x becomes harder. Right? But in 2's complement, it turns out it's relatively easy. All right, so I'm basically out of time. We should stop there. Don't forget, you have a midterm on Thursday. And so look on OnQ for the details of the test and links to old or sample tests.